Okay, let's see if you have W411. So W411 is exponent minus j 2 pi k, and your k is 1, your n is 1. So you have 1 times 1 over 4. So this is equal to cos pi over 2 minus j sine pi over 2. So cos pi over 2 is 0. So you have minus j. So this is for W411. So what happens if you have W412? W412. Same thing. You have to use exponent minus j 2 pi 1 times 2 over 4. So this one is equal to cos times 4 pi minus j sine pi. So sine pi is 0. So what's left is cos pi. Cos pi is minus 1. Okay, so you repeat this one until W433. Same thing, you apply the same technique. You will find 3 times 3 over 4. So you will have blah 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 blah. Okay, another way around, you don't have to find all the values. Okay, for example, you know that, okay, this one is from your linear algebra technique. Okay, so in your linear algebra technique, okay, first row, first column, definitely you know that the value is always 1. Why? Because of we have 0. So exponent 0 is 1. Okay. Okay, now you have to worry something inside here, starting from W411 until W433. Okay, this is meant for 4 by 4 matrix. Okay, so you know that W411 is minus j. Okay, so W41 is 1. Okay, so W421 is minus 1. Okay, so next you know that W31 is j. So what you have to do next is, for this one, oh sorry, this is minus 1. What you have to do is, you just have to do something like in linear algebra technique. Okay, we have symmetrical. Remember the symmetrical? Okay, so symmetrical of j is here. Symmetrical of minus j, you put here. Symmetrical of minus 1 is here. Symmetrical of here is here. So we have our symmetrical point here. So basically you just flip your value. Here similar to here. This value is same with this value. This value is similar to this value. This value is similar to this value. Okay, so basically you just have to find what is the value here for W for 01222. So W422, after you do the calculation, it is equal to 1. So it is 1. So basically you just have to find what is this value, what is the value for this one, this one, this one, and this one. This value is actually the symmetrical value. So this value is symmetric with this one. This value you can get from this one. This value you can get from this one. This value you can get from this one. Okay, so basically you don't have to find for all. Alright, so this one is only for 4 by 4 matrix. Okay, if you want to find for 3 by 3 matrix, you have to find by yourself. Okay, try at home how to get the matrix value, the matrix dimension for 3 by 3, 5 by 5, 6 by 3 by 6. Okay, find by your own. Okay. Okay, next we move to slide number 11. In slide number 11, it is on inverse DFT. Just now, I show you the matrix dimension, the matrix computation for DFT. Okay, in slide number 11, it is on inverse DFT. Same thing for inverse DFT. So inverse DFT is actually the inverse transform of your SK. So basically inverse DFT, you need to find your Sn. So how to find your Sn? You need to use this equation 1 over n k from 0 to n minus 1. This is n. Okay, so you have xk. Now here we have wn minus kn. Okay, why we have minus? Okay, this one I did mention to you just now. Remember? Okay, about how to get minus, how to find 1 over n. Okay, this one is coming from the previous slide. Okay, same thing. 1 over n for your matrix dimension, your SK is given from the question. Okay, you know from the question, let's say you have xk equal to 1, 2, 3, 4. The range of k is from 0 to 3. So basically this is your k. Oh sorry, this is your xk. And then from your xk, definitely from this range, you may know what is your capital N value. Okay, you have 0, 1, 2, 3. So your capital N value is equal to 4. Okay, so from this sequence, you may know what is your matrix dimension. Okay, your matrix dimension is 4 by 4. Okay, next, your capital N is 4. Alright, so now for your matrix dimension, okay, we have Xn and then you have 1 over 4 outside of your matrix dimension. So whatever value of your means after you do matrix multiplication, okay, you need to multiply with 1 over 4. Or, okay, after you find the value for each W for 4, something like this. Okay, this is W for 0. Okay, so next here we have W4 minus 1, 1. W4 minus 1, 2. W4 minus 1, 3. Until W4 3 minus 3, 3. Okay, even it is minus, you don't have to worry. You just have to apply the basic equation of W4. Same thing, WKNN, the same thing. Okay, you have, for example, Wn minus Kn. So this one is equal to S1m minus J. Okay. Okay, alright. Okay, sorry. Okay, let's see, we have WNKN. So we have exponent minus J 2 pi Kn over capital N. So if we have minus here, this one become positive. So if we have positive here, this one already become cos 2 pi Kn over capital N plus J sine 2 pi Kn over capital N. That's it. You don't have to worry so much. Okay, this is all about max. Okay, just now we have Wn Kn. Now for inverse DFT, we have minus. That's it. Okay, so what you have to do next is look at your slide. We have 1 over n. So, okay, whatever the values you get inside your matrix dimension, don't forget to times with 1 over n. Okay, times with 1 over n first, and then after you get the values, and then you multiply with your xk. Don't forget to multiply with 1 over n. Okay. Okay, in slide number 12. Slide number 12 is on the relation between DFT and DTFT. Okay, so this one is just to DTFT is given by, and then we have the equation for DFT. Okay, so basically, as I said before, DTFT is meant for two types of sequences, finite sequence and infinite sequence. But for DFT, we just concentrate on finite sequence length. Okay, why we need the finite sequence length? Because of the matrix dimension. Okay, so basically to solve DFT, of course, we have two techniques to solve DFT. One of them is matrix dimension. So basically, for you to solve the matrix dimension, definitely you must know the exact value of your capital N. So for you to determine your exact value of your capital N, definitely you need the finite length sequence. That is the difference between DFT and DTFT. Okay, clear? Okay. Next, we move to the theorem. Okay, similar to DTFT, in DFT also we have several theorems. Okay, same thing. We have linearity theorem, we have circular time shifting. Instead of we have time shifting, now we have circular time shifting theorem, circular frequency shifting theorem. Okay, and duality, same thing. Okay, so in DFT, since it is finite length sequence, we have, for example, 1, 2, 3. I use the same example. I use the same range here. Okay, when it is circular shifting, means the numbers will keep circulating. Okay, for example, when n equal to 0, so your x0 is equal to 1, right? When x1, the value is 2. When n equal to 2, the value is 3. But when x equal to 3, the value is, okay, this is the meaning of circular time shifting, circular time frequency shifting. Means we need to circulate the values. Okay, instead of we use zero padding, okay, in DTFT you use zero padding, right? So in DTFT, your SK definitely will be 0 because it is we use zero padding. But in DTFT, you have to circulate the value. Okay, this is when n equal to 0, 1, 2. When it comes to 3, when n equal to 3, it will be circulated. This value is keep circulating. So 0, 1, 2, 3, 4, 5. So your x3 is equal to 1. x4 is equal to 2. x5 is equal to 3. So this is for DFT. The value is keep circulating. Compared to DTFT, when x3, when your n equal to 3, your x3 will become to 0. x4 is also 0. x5 is equal to 0 because you need to do zero padding. That is for DTFT. Okay, for DFT, you have to circulate the sequence. Okay, clear? Okay, because of that, okay, for DFT theorem, we have circular time shifting, we have circular frequency shifting. Okay, so basically after this, I'm going to show you the example of circular time shifting and also circular frequency shifting. Alright. So for DFT also we have circular convolution theorem. Okay, so same thing. There is no big difference between DTFT and DFT as well. So same thing. We have convolution. Alright, so in circular convolution, same thing. We have convolve, and then when we have circular convolution, we have GK, HK, same thing. For modulation theorem also, okay, there is not much difference. Okay, slide number 18 is on the step on how to compute the DFT of real sequence. Okay, so how to compute the DFT of real sequence? Okay, let's say we have n-point DFTs of two real sequences using a single n-point DFT of complex sequence. Okay, so basically this is the keywords. Okay, you need to find the DFTs of two real sequences. Means, okay, we have two real sequences, for example xn and yn. Then you need to find what is the DFT of xn. You need to find the DFT of yn. Okay, so for you to solve, the keywords is DFT. Remember, when you have DFT, one of the technique is using matrix multiplication. Okay, in matrix multiplication, you just have, okay, refer back to the general equation of DFT. Okay, in that equation, we just have one part of your Sn. Okay, Sn times with the matrix dimension, remember? Okay, now we have two real sequences. So when you have two real sequences, definitely you have to create only one Sn, only one single matrix. Not single matrix, only one Sn. So how to get from two real sequences become one? So for you to create that, okay, you have to define a complex sequence. Okay, by means your first sequence will be your real sequence. Your second sequence will be your imaginary sequence. Okay, in slide number 18, point number 2. Okay, define Sn equal to Gn plus JHn. Gn is your first sequence. Hn is your second sequence. So you combine them, become one sequence. Okay, so become complex sequence. Alright, so where Gn will become Gk, Hn, DFT of Hn is Hk. Okay, from symmetry property of DFT of complex sequence Sn, okay, we know this is the equation. This is the two equation. Okay, these two equation will be given in the table of property during final exam, during your test. Okay, we will give you the formula sheet, so you don't have to worry. Everything is on the formula sheet. Okay, just that you must know how to use that. Okay. Okay, after you find, okay, the real and imaginary sequence, this is meant for point number 3, step number 3 actually. And then after you find the value for X conjugate symmetry, X conjugate antisymmetry, okay, you need to find what is your GK, what is your HK. Okay, just now in the question, okay, your first sequence is Gn, your second sequence is Hn. So definitely go back to the question. Determine the DFTs of two real sequences. Okay, so basically you have to find the DFT of Gn, which is Gk. You have to find the DFT of Hn, which is Hk. So how to do that? Okay, refer to this equation. Again, GK equation is actually conjugate symmetric equation. HK equation is actually conjugate antisymmetric equation. So basically, GK, why it is referred to conjugate symmetry? Because it is the real equation, the real sequence. Why HK is conjugate antisymmetry? Because your HK, first in point number 2, you assume HN as imaginary sequence, right? That's why in your HK, you need to use conjugate antisymmetric sequence. Why? Conjugate antisymmetric sequence is meant for imaginary sequence. Okay, how to differentiate between imaginary and real sequence? You look at the equation for conjugate symmetry and conjugate antisymmetry. For conjugate symmetry, we don't have 1 over J. But for conjugate antisymmetry, we have 1 over G. Okay? So basically, that is the difference. Okay? Note that if you look at these two equations, we have X conjugate minus Kn. Okay? So basically, X conjugate minus Kn. If you remember your chapter 2, okay, you need to do zero padding and then you inverse. But this time around, you don't have to do zero padding anymore. What you have to do is, when you want to inverse, you have to do circular shifting. That's why we have this open and close bracket. This one. You look at the equation, right? You can see this one, this bracket. Okay, so what is the value for that bracket? Okay, we have note that X conjugate minus Kn is equal to X conjugate n minus K, to show that the sequence is circulating. Okay, circulating something like this. Okay, in slide number 21. Okay, this time around, you need to find the two endpoint DFT of two real sequences using a single endpoint DFT. Okay, so what happened for this step? It is meant for, if let's say you have one long sequence. In previous notes, okay, in slide number 18, it is on endpoint. So basically, for endpoint, you have two real sequences. Okay, but in slide number 21, okay, this one two endpoint means you have one long sequence. So from one long sequence, okay, the step is actually similar to previous, but this time around, instead of you have one long sequence, okay, we don't want to do a long sequence. It is a very heavy calculation if you want to compute a very long sequence. So what you have to do next is you need to chop, you need to cut. Okay, cut your long sequence into two sequence. Okay, so basically you will have one long sequence become two short real sequence. Okay, so for you to do that, you have to assume first sequence will be your real sequence, second sequence will be your imaginary sequence. Okay, so how to do that? N equal, what happened for this step? For step number 2, you have to break this sequence become two real sequences. Okay, let's see, we have Gn and Hn. Okay, so what to do next? Okay, we need to assume. Okay, assume Gn is real sequence, Hn is imaginary sequence. Okay, so how to know? Okay, so we assume your Gn is equal to V2n. This one equal to V2n plus 1. V0, V2, V4, and V6. Range is from 0 to 3. This one is V1, V2 plus 1, 0 plus 2, 0 plus 1, V3, V5, and V7. The range is from 0 to 3. Okay, from these two discrete sequences, okay, then we create the complex sequence. Okay, and then we define what is your GK, we determine your GK, what is your HK. Okay, now after you get your GK and HK, okay, at the very beginning, this is your question. You need to find the DFT of Vn. Okay, so what you have to do next is look at slide number 23. Okay, in slide number 23, you have to combine. Okay, remember in our first slide, from long sequence you have to cut, and then you have to break your sequence, and then you have to do inverse, blah blah blah. Remember the words? Okay, so what you have to do next is you need to combine them together. Okay, means we need to combine these two, GK, HK. After we find, okay, you need to combine them. Okay, use this equation. Alright, so use the last equation in slide number 23. Vk equal to Gk plus W2 NK HK. So please make sure you remember this equation. This second equation you have to remember for this chapter. Okay? Alright, so that's all for today. Okay, we shall continue inshallah tomorrow with the example. Okay? Alright, so see you again. Thank you. Bye.